Some of you might find this video helpful. In this one, we're going over position versus time graphs. This is just going to be me talking over some of the slides that are included in the big ideas. On slide number 3, a couple things to remember with distance versus time graphs. Time is always and forever going to be on the x-axis. You will see units such as seconds, minutes, or hours on that axis. On the y-axis, the axis that goes up and down, distance will always and forever be there. You might see units like meters or kilometers if we're using the metric system. If we aren't, you might see units like feet or miles, all right? We can determine an object's position from a distance versus time graph, or you might hear me say a position versus time graph. You're going to see a line on that graph. Now, if we were to look at a specific point on that line, that's going to give us an object's position. So for example, at this gray point here, at the time 1 second, that object was at the 10-meter mark. Okay, here's another example. Again, a specific point on that line tells us our object's position. So when it was 3 seconds into this race, the runner was at the 30-meter mark. We can also determine an object's starting position, or if they had a head start in their race, by looking at what's known as the y-intercept. So the y-intercept is where the graph crosses over the y-axis. Notice I'm emphasizing y because it's over the y-axis. So in this case, we have this red dot here. That's where this graph crosses over the y-axis. So our object has a head start, or we say its starting position is at the 10-meter mark. Go to slide number 7. We can also determine an object's direction by looking at the slope of the line. Remember, slope is determined by rise over run, if we're doing kind of a mathy definition of it. It's how much change in the y there is compared to how much change in the x there is. That's an even more mathier definition of it. Slope, though, in generic terms, is just how steep the line is. If the line is sloping in a positive direction, which means it goes up and to the right, so it looks like this, that means that the object is traveling in a forwards direction. So as time goes on, the object is getting farther and farther away from the origin or the starting line. A graph can also have a slope that looks like this, right, where it is going down as it goes to the right. That's called a negative slope. And that means that the object is traveling backwards. So as time goes on, the object is getting closer and closer and closer to that 0 mark, okay? Now, we get into the definition of speed. Speed is the distance an object can travel in a certain amount of time. We can decide speed based on 2 different things. The first thing that we can look at is just like, is the slope of the line shallow or is it kind of steep? So notice on the left-hand side, the slope of this line is kind of shallow, whereas the one on the right-hand side is relatively steep, right? If these were hills that you'd have to climb, the one on the right would definitely be harder to climb compared to the one on the left. The steepness of the slope can help us determine an object's speed. So take a look at one like this. This graph has a relatively shallow slope. That means that the object is moving kind of slow, right? They're only able to cover 10 meters of distance in 4 seconds. Compare that to a graph like this one, where this object is able to cover 40 meters of distance in 4 seconds. They're able to cover a lot more distance in the same amount of time. This object is moving much faster. You might have graphs that have a slope that looks like this. It's a completely flat line. In fact, there is no slope to it. So what does that mean? That means that your object is not moving. As time is going on, your object's position is staying the same. Another way that we can calculate an object's speed from that line is to actually calculate the slope of that line. You're going to be using an equation, speed is equal to distance divided by time, or in your head, come back to those mathy definitions. It's going to be rise over run, all right? So take a look at slide 15. Let's say we wanted to calculate the speed of this object during these 2 different intervals. Before you even start looking at the numbers, you can kind of make some predictions about what you're going to end up calculating. Looking at the pink line compared to the yellow line, the pink line is definitely a little bit shallower compared to the yellow line. So when you calculate the speeds, you should see that the pink line is a little bit slower than the yellow line. So how do we actually calculate those speeds then and test that prediction? Remember, I said it's rise over run. So for that pink one, we have to calculate how much distance the object traveled and then how much time it took them to travel that. So for pink, they traveled 10 meters in 2 seconds. Let me do that again. Rise is 10 meters, run is 2 seconds. So we plug that into our formula. Speed is equal to distance divided by time. 10 meters divided by 2 seconds tells us that the speed during that pink interval is 5 meters per second. Now we want to calculate the speed during only the yellow interval. We're going to kind of pretend that the pink one isn't there anymore. We only care about the yellow. So for that yellow interval, the rise was from 10 up until 40. And then the run is from 2 seconds to 4 seconds. So what was our rise? Our rise was a total of 30 meters in 2 seconds. We plug that into our formula, and the speed is 15 meters per second. So does that actually match our prediction? Yeah, the pink line is definitely slower, shallower slope. They're only going 5 meters per second. The yellow one has a much steeper slope. They're going 15 meters per second. All right, if you need to, you can hit rewind. You can rewatch this. You can ask questions, do what you need to do. Let me know how I can help you.